Okay, hello everyone, and welcome to course on Mathematical Foundation for Industrial Engineering. So this course is designed to equip you with essential mathematical skills, particularly in a topic that called linear algebra. So this is a crucial topics on understanding several complex engineering problems. Okay, for the first weeks of this course, we will cover four key areas, including linear equations, Gaussian eliminations, which are fundamental techniques for solving linear systems, and then there will be discussion about matrix operations, which are the building blocks of linear algebra, and finally, property of matrix, where we will delve into deeper aspects of matrix theory. And in addition, we also discuss about something called elementary matrix. Okay, let's start with the linear equations. Basically, in a simple explanation, linear equations is relationship between variables where the power of each variables would be less than equal to 2. Means that, for example, this one, when you have two-dimensional variables in which you have two variables, unknown variables, x and y, well, you can normally draw it as a line in x and y rectangular coordinates. So it can be represented with a, which the coefficient a multiplied by x, here the power will be 1, b multiplied by y to the power of 1, and c is another constants that we have here. So basically, this would be representing a line when you draw a line in the x and y coordinates. So here, this line, for example, this one, is a representation of this type of equations. Okay, if you add more variables, when we have three dimensions or called three-dimensional variables, you can form a plane. Uh, Plane means that when you draw it in a rectangular x, y, and z coordinate, then this would be represented in this type of form. So when you draw it, this x and y coordinates. So you have another axis here, z, and let's say you have this line earlier, and this will be a plane that represented in the three-dimensional um, uh, variables here. So x, y, and z, all of this will be to the power of 1. So those are simple explanations about linear equations. So what if you have more than three variables? Here, you can still consider that as a linear equations that can be defined also with n number of variables, when n can be 1, 2, 3, 4, and many. So this as linear equation systems can be represented as the equation form such as follows. So a1x1, this will be the coefficient for variable ones. This will be the first variables up until an multiplied by xn equals to b. In case where you have the b is equal to 0, then you will have formulations look like this. Well, of course, you may wondering why should we concern about linear algebra, especially linear equations, which we discussed earlier, where this concept were some of the building blocks where will be used later on when you talk about a more complex engineering problems. Take example here when you have an equations of between two variables, then you are going to try to find, okay, when you have some things represented in these line with these two variables, can we find a solutions that represents these two unknown variables? Okay, so in order to do that, you need to learn on how to solve these two linear equations in order to find the variables of x and y. We call that as finding the solutions for these two linear equation systems. Okay. Um, for a linear equation systems, it means that basically find whether these two lines were having intersections in when we draw it in the graph, or in when we illustrate it in the x and y plane coordinates. So without knowing the exact value of the coefficients as well as the variables here, when we try to find the value of these x and y variables, there will be three possible outcomes here. First, when these two linear equation system have no solutions, mean that they have not intersects one to another. For example, if this one is the line 1 and this one line 2, there is no intersection between these two lines, so that means that you cannot find a solution for these two linear equation system. Another case is that when you have this the first line, for example, and the second line intersects at some point, so it means that you can find, okay, what is the value of y to exactly particular point, and what is the value of x to fulfill these two equations. And the third possible outcome would be this one: when you have both line were intersects at all of their point, means that these two is actually coincident lines. It's equal to line that have intersection at all of that point. It means that also it is the same line. Okay, here is the explanations that describe what I've discussed in the previous slides. So there are three options. The first one is this one, where you have two lines which doesn't uh, which is parallel. It has consequently it has no solutions. Second one is this one, where you have lines that intersects in one particular point. And finally is this one, the third one, when you have that lines that coincide with one to another, so they have infinitely many points of intersections. Consequently, it also have infinitely many solutions. Okay, this slide introduces us to augmented matrix and elementary row operations. So these two metrics were crucial tools in linear algebra. So what is augmented matrix? Augmented matrix basically combines the coefficients and constant of a linear systems into a single matrix. For example, here, the first figure, we have representations of linear equations with and variables as shown in here, right? So later on we will need to understand how to convert this into an augmented matrix form of it. This is called augmented matrix forms. um, so basically later on this augmented matrix form will be used to to perform an operations called elementary row operations, which several operations that we can do to help us to find a solutions for linear equation systems. So basically elementary row operations consist of some things called row switching, and then there is row multiplications, and there is also called row addition. Okay, these operations are used to manipulate the matrix, so it is easier to solve or easier to find the solutions. Typically, it's the end solutions of this matrix when it is being manipulated. Okay, this augmented matrix will be reduced into something called the echelon form of it, echelon form, or reduce echelon form. Okay, you will learn about that also again a little bit later in the slides. Okay, so in this slide we will delve into practical example of augmented matrix and how we can perform elementary row operations. So we will take a look at specific linear equation systems, for example this one, and then we uh, uh, first convert it into its augmented matrix form of it, and then we will perform several elementary row operations on this, including swapping rows, multiplying rows by a non-zero constant, and then adding a multiplied row into one into another. So through these examples, you will see how the operations are used to simplifying the matrix and make it easier to find solutions of the linear equation system. So first, in order um, to convert from the linear systems to the augmented form of it, augmented matrix form, matrix. So you can see here, uh, when here we have each column will represent move here to the augmented matrix of it. So it's this one corresponding to the first each so this will be corresponding to x variables, y variables, z variables, and this is the right hand side of the matrix. So each of these will be taken from the coefficients of each variables in the first equation, second equations, and then the third equation, or we can call it also first row, second row, or third row. Okay, and then after we have these augmented matrix versions, uh, our task is to perform elementary row operations to this augmented matrix. But the question is, what kind of row operations we need to do? Okay, later on, you will thought in order to make the augmented matrix simpler and easier to find the solutions, you need to perform up until it becomes the echelon form of it. Okay, so for now, keep that in mind. We will transform it into its echelon form. But since you are not yet being explained what is echelon form, just follow the explanation along the way. Okay, so first come is that in order to make it into echelon form, we will try to mix all of the diagonal of the matrix become one. It's one, 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 and then all of the um, value below these diagonals will be zero. This one will be zero. This one will be zero. This one will be zero. Okay, those are the echelon form of it. Okay, so now if you see here, you see that this one, the first row, okay, the diagonal is already one, so you keep that. Okay, but you see here below is still two. Okay, so let me erase first. Okay, we want to make this become one. Okay, what can we do? in order to make this one become 1, remember we have several elementary row operations. Elementary row operation, we have matrix multiplication, and then matrix switch, and then matrix addition. Okay, in order to make this one become 0, one of the way is that we can add 2 multiplied by the first equations or the first row to the second row. So we can perform row 2 will be equals to 2 minus 2 multiplied by row 1 plus the original row 2. Okay, so here you can see that, okay, this one 2 plus minus 2, so you can see, let me draw it here. So let me erase, and then when, okay, we will perform the new row 2, okay, will be equals to minus 2 multiplied by the original row 1 plus by the original row 2. So if you see here, the original row 1, this one row 1, right, row 2, row 3, okay, original row 1, if you multiply this by minus 2, so you will have minus 2, and then minus 2 minus 4 minus 18, right, and you will plus it with the original row 2, 2 4 minus 3 1, so you plus this one, okay, then it becomes 0, and then this will come 2, and this minus 7, this one minus 17. This will be the new row 2. Okay, see this one, it will replace the row 2 here, right? So this replace it here. Okay, then this already becomes 0. Next task is make this one become 0. How do you do that? Okay, you can do new row 3 will be equals to minus 3 multiplied by row 1 plus original row 3. Then you will have something like minus 3 minus 3 minus 6 minus sorry, minus 19 minus 27, yeah, and then you will plus it with the 3, it's minus 2 minus 27, and then you will plus it with the 3 6 minus 5 0 plus, this becomes 0, and this become 3, and then this become minus 11, and then become minus 27. Okay, we can see this result, row 3, it will replace this row 3 here. Okay, this replace here, you can see it in the next slide. Yeah, you can see this is the new result of our previous calculations, and continue with those. Keep in mind that, okay, we want the diagonal will be equals to 1, right, 1. So what should we do next? Okay, we do next is to make this one become 1. How do we do that? We remember we have 3 type of row elementary row operations. Number 1 is switching, number 2 is multiplying, number 3 is addition row with one to another. So in this one, what do we do is the new row 2, okay, the new row 2 will be equals to half by its original. So when you have this one, you will have the new row 2 is equals 0 1 minus 7 per 2, and then minus 17 per 2. So this one replace the original row 2 here, see here, and this one also here, right? Then what's next? Make this one become 0. How do you do that? So here you see this one already 1, so the new row 3 will be equals to minus 3 times row 2 plus the original row 3. Okay, then you get this one will be equal this. Okay, and finally you just need to make this one become 1. This one become 1. So the new row 3 will be 2 minus 2 times the row 3. Okay, you will get the new one here. See, now you have the all is equal 1. This is called the echelon form of the equations, or it can be shown here. With this form of echelon, it already so easy when you can see that the z value is equal to 3, and then you can substitute it to up here with 3, put it here, do you get the y value, or you can do continue the operations, make it become the reduced echelon form. This is called reduced echelon form, where in not only this diagonal equals 0 and below of it, this diagonal equal 1 and below of it is equal to 0, but up of the diagonal all equal to 0. So here you can see that the solutions of these equations will be x equal 1, y equal 2, and z equal 3. Okay, then you can plug these equations into the original equations, then you can find that this is a feasible solution. Okay, here we would like to explore what do we call as row echelon and reduced row echelon form. Basically, you need to understand these two forms in order to use the methods that we are going to use later, called Gaussian eliminations, which basically a form that is we intended the um, elementary row operations generated. So after you do several ERO, elementary row eliminations, you want the matrix that you have in the augmented matrix to become this form. Either it's a reduced row echelon form, or it's a row echelon form. Basically, first, for both, you need to identify this. This is called the leading one. Leading one. It means that the first, the value of for each row, this one, the value of variables that equals to 1. For example, this one, the value of the leading one is 1. So for a row echelon, reduced row echelon form, all the value below the leading one and above the leading one, because this one is the top one, so you don't have the one that above it. So all the value of this will be 0. That look like this. So for the second row, the leading one is this one, and all the value above and then below is equals to 0. And then the third row is this one, and this one will be 0. And the right hand side is uh, the right hand side value is not concerned in the reduced row echelon form, because up until here you already know, you can see, right? The value of z is equal minus 1, the value of y is equal 7, and the value of x is equal 4. Right? So you want it to be in this type of form in order to understand that, oh, I will know the uh, the value of the xyz already here. Okay, So this one also, this row 1, this is the leading one, this should be 0. Row 2, this is the leading one, this is 0, 0. Okay. Row 3, okay. For this one, if you convert, this is only two variables actually. So, and this is the right hand side. So this is doesn't matter actually, and you already can generate the value of these uh, two variables for this matrix, right? And then for this one, this is the leading one, x, y, z, maybe alpha. uh, this one and this one below is 0. This one, and then the second row is this one. This is 0. This is 0. The third row and fourth row doesn't have the leading one, so so you're already okay with it. Then this is the right hand side, and the value is not really our concern. And for this one, all the is leading there is no leading one here, so uh, it's already considered as the in its reduced row echelon form. Okay, now the other form that also uh, uh, we need to know called row echelon form. Okay, the difference between row echelon form with the reduced row echelon form is that when you have the leading one, you only consider what's below it. What above it, this one, you don't really need to consider it become 0. Why? Because sometimes when we do elementary row elimination, okay, for one particular methods or another one, we reduce it only up until its row echelon form, because it will take so long when you make it to become the reduced row echelon form. So you up until the row echelon form only. So for this one, xyz, right? So you will have the formula become uh, z is equal to 5, y plus z, y plus 6z is equals to 2, and then x plus 4y minus 3z is equal to 7. So you just need to substitute it back there, you got the value of the xyz. So there is another extra steps need to be taken in order to uh, uh, get the solution of row echelon form, not directly like this. Okay, so here also this leading one, and then below it is 0. Leading one below 0. This one is doesn't matter, no, if not 0. Right hand side is fine if it is equal to 0. So this one also, this leading one, the 0 is okay, okay, okay. This one, yeah, this one, because this row, this is the leading one. Okay, this row doesn't have the leading one. This one already the right hand side, so it doesn't matter for that. Okay. Important because later on when we learn about a method called Gauss-Jordan elimination, this method we need to understand whether it's our operations in order to following this method is finished is based on whether we already arrive at the row echelon form of matrix or not. Okay, or sorry, so the reduced row echelon form of it or not. So again, to illustrate again, what are the uh, row echelon form and reduced row echelon form was that, for example, here a matrix in a row echelon form has 0 below each leading one. Leading one means that in the diagram. Okay, this all is leading one. Whereas reduced row echelon form has 0 for above and as well as below of the leading one, or the diagonals that equals to 1. Thus, any real numbers substitutes for the, here we put a star, will be considered as row echelon form. For example, here the leading one is this one, so all this one could be a number that is not equal to 0, it's fine. For here we have 3 leading ones, this one all could be some number. Okay, for this one the same, for this one this is the leading one, and here all is not 0. The leading one is the first value is equals to 1 in that particular row. But for reduced row echelon form, all below and above of their leading one, it should be equals to 0. For this one here 0, this one 0 0, this one 0 0, but this one no leading one, so this one is okay to be not 0. Okay, so here 1, this one 0 is okay, this one 1 0 0 here, no leading one, so this one okay to be some value, to have some value. Okay, hope that would be clear about echelon form as well as reduced row echelon. Okay, now we'll cover the method, where methods to solve a linear equation system, where we use to those that we learned earlier about echelon form, when we will reduce this one into its reduced row echelon form. Okay, so first of all, uh, the step one is we need to locate the leftmost column that does not consist entirely of 0. Okay, so you can see here we had this one 0. Okay, this should be 1, so this or this can be switched to either this one. Okay, so in this one we select the second row, the row number 2, to interchange with the top row. Okay, so number 2 is switched with the row number 1. So so you can see here, this one row number 2, this one row number 1, we switch their position and become this new matrix. Okay, and then we want the first row to have leading one, this one will become to 1. So what do we do is that we will multiply this one, the new row 1, the new row 1 will be equals a half of the previous row 1. Okay, so 1 divided by AA means this matrix, this coefficient, so we get this one, new one. Okay, and then we want to make, all below the leading one will be equal to 0, so this one is 0, right? So what should we do is that add this one, row 1, row 2, and row 3. So the new row 3, okay, will be equals to 2 minus 2 multiplied by row 1 plus row 3. Okay, so then you will have this one. So this one becomes 0, this one becomes 0 again, so this one become because minus 10 plus 10 plus minus 5 is become 5, and this one 6 minus 6 plus 6 is 0, this one minus 12 plus minus 5 is minus 17, correct, minus 14, sorry, minus 28, plus minus 1 is minus 29. Okay, and then okay, continue from the previous step. Now the leftmost non-zero columns uh, of the second row, and the third row will be this one. Okay, so for the first row we already have this one, right? The leading one, and you have it already below it is 0. Next we want to make this one become 1, so the new value of uh, 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 the row 2 will be equals half of the original's row 2, and it will become this one. Okay, um, next after you have this leading one, so you want to make this one become 0. Yeah? So in order to make this one become 0, what you need to do is you can have the row 3, new row 3 will be equals to minus 5 times row 2, this one row 2, plus the original row 3. So you will have this value become 0 like this. Okay, 0. Okay, and then you want to this one already 1, right? So now you go back to the to make this one is become 1. Okay, so you make sure first all the leading one, and then make sure what below the leading one is 0. That's the first step you need to do. So this one, now the row 3 will be, the new row 3 will be equals 2 times the original row 3. Then you will have this value become 1. Okay, now all the leading one is complete, below it is already 0. Okay, this one is already at their row echelon form, not reduce row echelon form, because the above of the leading one, this one and this one, is still have value. Okay, next after it's become the row echelon form, you can continue to up until to make them become the reduced row echelon form. Okay, well, actually, as I mentioned before, up until here you can already find the solution of the value of the maybe this one, z, y, x, v, w. Okay, you already can find the value x, v, w, x, y, z by substitute it back to the original formula. But now we try to make it become reduce row echelon form to make it easier to get the value of this unknown variables. So now in row echelon form, you already have this value. uh, in order to make it reduce row echelon form, you can substitute it back, start from the last non-zero rows and work it upward. Okay, add suitable multipliers for each row to the row above. So previously we go from top to bottom, now we go from below to top. Okay, um, okay, in previous one, what you need to do is the row 3, row 2. Before this one have value, right? Now after you do the row 3, you can go back to the previous slides to see it. The new row 2 will be equals to 7 per 2 original row 3, plus the original row 2. Then you will get this new value for the row 2. Okay. And then after this, you want to make this one become 0. What you need to do is the new row 1, this one, R1, new row 1 will be equals to, yeah, this one 6, right? So this one you multiply by minus 6. Minus 6 multiplied by row 1 plus the original row 3. Then you will have this new row 1. Okay, with this value is equal 0 already. And then finally, the next one is this one, the leading one. So you want to make the above it is become 0. So what you need to do is the row 1 from this augmented matrix, the new row 1 will be equals to 5 times, because this is minus and this is positive, 5 of the row 2 plus the original row 1. Then you will have this new row where the value of the third row for the new row 1 is 0. And then after you check this one, leading 1 below is 0, leading 1 above and below is 0, leading 1 above and below is 0, right? Here you can already get the value of the solutions. Okay, now we continue with the Gauss-Jordan elimination approach. Previously we already tried when we have the reduced row echelon form of it. We can understand what is the value of the variables, right? X, Y, Z, right hand side. And here when it is reduced row, so Z is equals to -1, Y is equal 7, X is equal 4. Okay, same here. This is X, Y. This is right hand side. And this is leading one. So so this one will be X will be 0, Y will also be 0. Okay, so that's how you use the reduced row and row echelon form of it. Continue. When you're being asked to use the Gauss-Jordan elimination, first thing first is that you need to able to convert these linear equations to become the augmented matrix version of it. Okay, so for example, this one will be 1x1 plus 1xy, sorry, x1, x2. Let me delete it first. This one x1, x2, x3, x4, x5, x6, and then this is the right hand side. Yeah, so you want to have the x variable here, x1 until n, and this one is the right hand side. Okay, you see right hand side, the first equations, row 1, row 2, row 3, row 4. Right hand side here 0, -1, 5, and 6, right? This one x1 is 1, 3x2 minus 3, x3 we don't have x4, so it's 0, 2x5 we don't have x6, so it's 0, right? So here also 2 x1, 6x2 minus 5, x3, and so on. Yeah, you can complete it like this. And then what you need to do is first each row find the leading one. This one, for example, O is already reading 1, then you need to make below it become 0, right? Okay, so this one already, then this one becomes 0, so the new R2 will be equal to -2 multiplied by row 1 plus the row 2. So you have the new R2 here. Sorry, this one row 1, this one row 2. This will become 0. Okay, and then this one also become 0, right? So you wanted the new R4 will be equals to minus 2 R1 plus R4. So now this one, the new R4 is also 0. What comes to the rest of the variable, rest of the constants here, coefficient here is also follow. Okay, next one, you want to make this one become the leading one. So the new row 2 will be equals to minus 1 multiplied by original row 2. So you have here the new row 2, 1. Okay. And then you already have this one become 1. This would be 0, right? 0. So what do you need to do is the new row 3, okay, new row 3 will be equals to 5 multiplied by row 2 plus the original row 3. So you have this one become 0. And then this one, row 4, the new row 4 is equals to 4 multiplied by row 2 plus original row 4. So you get here this one row 3, this one row 4 becomes 0. Okay, next you need to check, okay, this one row 3 all 0 already, no need to have leading one. This one you need to convert to a leading one. So the new row 4 will be equals to original row 4 multiplied by 1 per 6. Okay, so this will become 1, this will become 2 per 6 or 1/3. Okay, see, you have this one become 1, this one become 1/3. Okay, this is called forward phase. Okay, forward phase is make leading one below it 0, leading one below 0. Now you are continue to make it become backward phase. Okay, backward phase is that making all above the leading one, start from the last leading one, this one for example, become 0. Okay, become 0, and then next this becomes 0. Okay, so for this one you start from here, this you want to make it become 0. So the new row 3 will be equals to what, this one, 1 2 3 4, sorry, new row 2 become the minus 3 multiplied by row 3 plus original row 2. Then you will have above this one is become 0. Okay, and another one is this one. Okay, the new row 1 will be equals to 2 times multiplied by row 2 plus original row 1. So this row 2, this row 1, so this above this one becomes 0. Okay, then we have complete so-called backward phase, where all above the leading one is equal 0, and below the leading one from the forward phase still 0. So here you already can conclude that this one z variable y x this one u v w, or oh, you can use this one x1 x2 x3 x4 x5 x6, so like the one we have earlier. So x6 equals to 1/3, um, x, what is this one, x3 plus x4 equals to 0, and then x1 plus x3 so x3 plus 2x4 equals 0, x1 plus 3x2 uh, plus 4x3 4x3 plus 4x3 plus 2x5 equals 0. Okay, so this is the value, okay, the solutions that you can find. Okay, see, like what I have put right earlier. So note that these constructions, the linear system in tree can be ignored because we have all the 0 rows. Okay, um, so the corresponding solutions will be this one. Okay, so you put back all x1 minus 3x2 for x4 and minus, and then x3 is this, x6 is this one. So finally, we can express the solutions with because this one, what will be the value x2, x4, x5? Well, it's arbitrary, okay, because it's still unknown. So you can put some parameter, let's say change it with the r, s, and t. So you can have this one, x1 is equal minus 3 uh, r minus 4s minus 2t. So later when you put the plug the value of x2, x3, yeah, and then x4, okay, you can get the value of x1. Okay, for x5 you put it is a parameter value of t, and x6 is obvious, is 1 per time. Okay, that's how you write this answer in mathematical form. So you still have a parameter that you need to decide what will be the value of x2, x3, x4, and x5. Then you can get x1, and but for the x6 is already given. Okay, I think that's somewhat summarize what is Gauss-Jordan eliminations. This video plug here, you can watch. This is from YouTube. It's a more complete explanations on how to use Gauss-Jordan eliminations up until the reduced row echelon form. Okay, we now turn our attentions to matrix and its operations. These slides will introduce you to the basic of metric operations, including addition, subtractions, multiplications, and many things. So understanding these matrix operations is a crucial part on where you can manipulate a matrix in linear algebra. And for example, first of all, we need to know that here are several types of matrix. This is uh, matrix with 2 by 3, means that 2 columns and 3 rows, and then this one is 4 by 1 matrix, and this one is a 3 by 3 matrix, and then this one is a 1 by 2 matrix, and then this is a 1 matrix that also can be considered as a scalar, uh, but no, this one is a matrix. So we will use normally a capital letters to denote matrix, this one, and a lowercase letter to denote the numerical quantities or the value inside of this matrix when you don't know the real value yet. So this, when it's capital, normally it symbolizes a matrix. A matrix bracket are often omitted for a one by one, like this one is sometimes rewrite just one, making it impossible sometimes to tell whether it's a symbol of a number 4 or it's a matrix 4. So this is really cause a problem because we can understand it by its context. Okay, in this first slide, sorry, earlier I am explain it to you a little wrong. Normally we denote the matrix by this one is the row and this one is the column. So 3 by 4 matrix when we have 3 rows like this, 3 rows, and then this one is 4 columns. Okay, and we can denote the entry of a matrix like mentioned earlier. The matrix itself is in capitals and the entry itself in small letters, and this index I and j normally a subscript here, where this subscript represent the locations in the matrix. Let's say for example A11 is the one on the top left, and then A34 is the one that on the bottom right. Okay, so M by N or row and column matrix. Um, so normally we can also write the matrix as like this. Is a M by N matrix or Aij. Okay. Then the entry, oh yeah, as I explained, I and j of a matrix as commonly denoted as this one, those matrix above. Okay, so for example, if you have a matrix a 2 by 2 like this, so the entry of this value is equal to, or you can write as a11 is equal to 2 as well. But if you want to use the matrix form, this would be the notation of it. Okay, and so on. A1 2 is this one, row 1 column 2 this one, to A21 row 2 column 1 this one, A22 row 2 column 2 this one. Okay. Row and column factors are very special, have very special importance, and it is common practice to denote them as a bold-faced lowercase letter rather than the capital letter. For such entry, double subscripting of the entry is unnecessary. Thus, a general 1 by n row and m by 1 matrix can be written as like this. So A, this one which will be the row matrix, this one is the column matrix. Okay. And another important part is when you have n by n row and columns, we call that one square matrix with the order of n. So 2 by 2 matrix is a square matrix with the order of 2. 3 by 3 matrix is a square matrix with the order of 3. And this one, n by n matrix, you will have like this with the order of n, and the main diagonal will be the one that has the same subscripts in the index here, where I equals to j is the diagonal. Okay, these slides focus on the concept of matrix equality. Well, we will define what it means for two matrices are to be equals. Um, it is called to be equals if they have the same size. Okay, size this one, whether it's m by n, this m and this n is equals, and the corresponding entries or in the value inside of it is are equals, all the value is equals. So the matrix, this one A or this one or B and this one is expressed to be equals like this. Aij is Bij or this one. Okay, and you can consider this matrix, this one and B, okay, and C. Okay, if the value of this x is equal to 5, so you will have 2, 1, 3, 5, and this one A, and B will be equals to 2, 1, 3, 5 also. And this one we call the matrix A and matrix B are equal because they have the same size and has the same value for each A and B. But if the x is not equal to 5, then A will be not equals to B. Okay. And then, well, for A and C, okay, when whatever the value of x for A and C, whether it's 4, yeah, we will never have A equals to C. Okay, A always not equal to C because they have different size. Yeah, A is a 2 by 2 matrix, C is a 2 by 3 matrix, so it's never be equal. Okay, next this slide focus on the addition and subtraction of a matrix. So when you have two matrices with the same size, okay, with the same size, okay, let's say this one matrix A and B, both are with the size of n by n, m by n. Okay, in order to add these two matrices, you will just need to um, uh, add the value of the same index, okay, for each entry. So for example, the value of this one for A equals to B will be A11 plus B11. So this one will be A12, B12. Okay, the same concepts were applied for subtractions. Whenever you have the same matrix of A and B, the matrix with the same size of A and B, m by n, yeah, this one. So you, in order to subtract it, A equals to A minus B, so the value of the corresponding entries for the same index will be the equals to the subtraction of it. So for example, the subtraction, the value of this one, let's say it's a matrix C, so C11 will be equals to A11 minus B11, okay, like this one, and so on. Okay, and in this slide it's an example of matrix addition and subtractions. You can see that in this example we have three matrices A and B where they have the same size. It's a 3 by 4 matrix. Okay, and then when we calculate A and B, A plus B, it will be equal like this. So like for example this one, minus 2 is equal 2 plus minus 4, so it's equal minus 2. And this one 4 is equals 1 here plus 3. Okay, and you can calculate the rest of it. For A minus B, yeah, the same. So this one will be equals to 2 minus 4, so you get 6. And this one is equal to 1 minus 3, so it's equal to minus 2. Okay, so this is the how to calculate addition and subtraction matrix. However, for A plus C, A, B plus C, A minus C, B minus C, it's undefined because the size of the matrix is not the same, so you cannot uh, add and subtract matrix that is not in the equal size. Okay, different with addition and subtractions. Now we talk about multiplication. First, we talk about scalar multiplication. Scalar multiplications is a multiplication of a matrix, let's say matrix A here, with a scalar value, a value of C. Then this is called the product of CA. Okay, when you multiply CA, C scalar with a matrix. Okay, so basically we obtain this multiplication, scalar multiplications, is by multiplying each entry of a matrix A by C. So multiply by scalar. Okay, so then you will have each entry will be equals to C multiplied by Aij. Okay, so for example, here we have matrix A, matrix B, matrix C, and then you want to uh, multiply it with a scalar. Let's say 2 multiplied by A. So you have 2 multiplied by here, 2 multiplied by 3 multiplied by 4, 2 multiplied by 1, 2 multiplied by 3, 2 multiplied by 1. So you have 4, 6, 8, 2, 6, 2. Right? What about this one, B? If you multiplied it by minus 1, so basically you multiplied minus 1 by multiplied by 0, by multiplied by 2, multiplied by 7, minus 1 by multiplied by minus 1, by 3, and by 5. You will get this one. Same with this one, 1/3. Okay. Okay, it's also common practice when you have minus 1 multiplied by B, you can call it minus B. Okay. Okay, now we go to the different concept about multiplications. Previously, we talked about multiplication with scalar. Now we multiplied it by another matrix. Okay, matrix multiplied by matrix. So in this one, what you need to know is first is that when you multiplied a matrix A and multiplied with matrix B, we will need to make sure the size of it. Okay, let's say matrix A and matrix B have the size A is M multiplied by R. Okay, and then B is R multiplied by N. So this is the row multiplied by R column. This is row multiplied by R column. Make sure this will be equal to this one. Okay, so that you can multiply it together. Then you will have a M by N matrix. Okay. So this is called the product of AB. When you have matrix A is M by R, N is R by N, then you will have AB is a M by N matrix. Okay. So in order to multiply it, first you need to multiply the corresponding entry from the row and the column together. And then it add up to the resulting products. For example, here you have an A matrix and B matrix. So this is the same 3 by 3, right? 3 by 3. So you will have another 3 by 3 matrix AB. When in order to multiply this, you will have to multiply the this row multiplied by this column. Okay, and you get the entry for this one. Okay, so this one though 1 1. Okay, this one 1 1, this one 1 2. Okay, index 1 3, 1 4, sorry 2 4, 2 1, 2 2, 2 3, and then 3 1, 3 2, and 3 3. Okay, the index 1 1 will be equals to A multiplied by J, this one, the first one multiplied by the first one, B multiplied by M, okay, this one multiplied by this one, and then C multiplied by P, C multiplied by P. Okay, what about the second entry? Okay, okay, 1 2, so you still this one row, okay, this one 1, now column 2, this one. So here you will have A multiplied by K plus B multiplied by N, this one, and then C multiplied by Q. Okay, so that's how you multiply the two matrices. Okay, this is an important concept because you need to carefully take a look at step by step of the calculations, and by understanding this multiplication of matrix, you will be able to use it to several things that you can use later. Okay, yeah, here We continue with the example of matrix multiplications, and we will go with the calculation of step by step by illustrating it how to multiply matrix and by aligning row and columns of the sum of the products. For example, first we need to check matrix A. Let's see here, it's a 2 by 3 matrix, and matrix B is a 3 by 3 3 by 4 matrix. Okay, so here you can see that, okay, if we multiplied A and B 3 by 4, 3 by 4 matrix, so if you multiply the A and B, so you will have this one, this is equal, right? Okay, so you can multiply it together, then you will have 2 by 4 matrix. Okay, so you will have something like this. Okay, it's a 4 value here and two rows here. Okay, so just like this one. Now if you want to have the what is the value of each of these, so for example, this one, what is the value of this one? So this is 2, 3. Okay, so you will need to multiply the uh, the 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 value of wait the value okay, the value of the second row with the value of the third 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 column here, this one. Okay, so 2 multiplied by 4, okay, 6 multiplied by 3, and then 0 multiplied by 5. Okay, this one you get 8, this one you get 18. Okay, so this one 0, so you have 26. Put it here. What about this one? How do you calculate it? Okay, this one is 1 1, so you multiply with the row here with the column 1 here, so it should be 1 multiplied by 4 plus 2 multiplied by 0 plus 4 multiplied by 2, so it's a 4 plus 0 plus 8, so it should be 12. Okay. Okay, this slide we have the continuation from the previous example, where for each entry you will need to calculate the value of it. For example, this entry, the calculation is this one, so it's basically using this row and this column. Okay, and then for this entry you will have this one, this one multiplied by this one. Okay, so and so on, so you will get this, all the entry of this matrix multiplications. And next concepts is about the transpose of a matrix. Well, it's formed by turning all the row of a given matrix. Let's say you have this one, you 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 turning all the rows of this matrix into the column, and vice versa, the column into to its um, um, row. Okay, so for example here, okay, so you have row here A B C, it become the column here, row here, so become the column. Okay, and the symbol of transpose is this one, uh, superscript of T. Okay, so you have A B C D matrix, so when you transpose matrix A, you see here the row of the matrix become the column. Okay, so means that when you have a 3 by 4 matrix, you later ends up with a 4 rows with 3 columns matrix. Okay, Here also the same, you have a 3 by 2 matrix. Here you have a 2 by 3 matrix. When all the rows transpose into a columns. Okay. Yeah. Yeah. Okay, here you have 1 by 3. This one become a 3 by 1 matrix. Okay, but for a 1 by 1, it's still equals to 1 by 1. Okay. Now we talk about identity matrix. Identity matrix is denoted as a I matrix, where you normally have is a special kind of matrix where all the elements of the main diagonals, this one main diagonals, is equals to 1. So this is a matrix of 2 by 2. Okay, then the main diagonals will be equals to 1. This one a matrix of 3 by 3, the main diagonals will be 1. Okay, so when you have identity matrix, it should be an n by n matrix. Okay, then when you multiply the a multiplied by b and b multiplied by a, okay, which equals to when you have a matrix, then you multiply it together, yeah? And when you multiply it the opposite way, a multiplied by b, b multiplied by e, it's normally not equals, but when it's equal, then it means that when equals to identity matrix, then it means that you have a matrix which were inverse to each other. So B will be equals to inverse of A. Okay, this is another terminology in matrix, inverse of a matrix. Okay, here we talk about the inverse of a matrix, where normally denotes as A superscript of -1. This is read as an inverse. Okay, not a power of -1. It's different. For a matrix, this is an inverse. It's a unique matrix that when you multiply it with the original matrix A, so when you multiply A with its inverse, you will have identity matrix. Okay, the one that we just said earlier. Okay. Uh, for findings the inverse of a matrix, normally it involves several swapping some element and changing sign of the others for a 2 by 2 matrix. But for a larger matrix, usually it will involve transform it into the identity matrix while simultaneously applying the same operations to an identity matrix that we obtain to inverse. So we will show this concept later. So how to find an inverse using operations to the identity matrix. But for now, this is the formula that you can use to find an inverse of a matrix of a 2 by 2 matrix. Okay. For example, uh, um, here we have a 2 by 2 matrix of A. In order to find the A inverse, you can use this formula. 1 divided by A multiplied by D minus by B multiplied by C. D swaps this one. Okay, A, D, A, and then for this one, change the sign for this entry. Okay, so basically A inverse will be A per this one, the value of A, and adjacent, this one called adjacent matrix. So when you swap the the value of A and D and change the sign of B and C, called adjacent matrix. Now try to use this formula to find this matrix. So it will be equals to 1 divided by 1 multiplied by -3, okay, per minus B multiplied by C, -2 multiplied by C. C is 2. Okay, and then multiplied by matrix when we swap A and D, 3 -3 and 1, and then you change the sign of B and C, 2 and minus 2. Okay, so the calculations will be looks like this. Okay, then you will get this value, and this is the inverse of a matrix of 2 by 2. Okay, and then actually we can check if this formula works by using the operations that usually calculate for a larger matrix. So you have, this is the original matrix, okay, and this is the identity matrix, right? Identity matrix for a 2 by 2 matrix is C1 0 0 1. Okay, when you try to turning this into the matrix that's identity here, this matrix become identity matrix, and this one will be the inverse. Okay, so let's try to do that. First, to make this one become identity matrix, of course this already same, right? So same to now you make this one become 0, and then this one become 1, this one become 0. Okay, in order to do that, we can do row operations. For example, first you multiplied by row 1, this one row 1, by minus 2. Okay, and then add it to the row 2. Okay, so the new row 2 here, yeah, we want to make it, this one becomes 0, right? So it will be equals row 1 multiplied by minus 2, okay, plus the original row 2. So you have minus 2 4 uh, minus 2 4, and then uh, minus 2 0. Okay, and then you plus it with the original row 2 2 minus 3, and this one would be 0 and 1. You plus it here, 0, and then uh, 0 and then 1, and then minus 2 and then 1. Okay, then this will be your new row 2 that you put it here. Okay, see the same. Okay, and then now you have this part already equals to identity matrix, this one already equals to this one also already, but this one is not. So how do we make this one become 0? We can do it like the new row 1 will be equals to 2 multiplied by row 2 plus the original row 1. So we have 2 multiplied by row 2, 0, 2, minus 4, and 2 plus the row 1, 1 minus 2, 1, 0, plus 1, 0, minus 3, 2. So this one will be your new row 1 here. Okay, this one, you see, is equal to this, right? So now you have on the left side this one, the original is A, now it's become the identity matrix, and this one is the new matrix that we found. This will be the A inverse. Okay, so the A inverse is equal to this, which will also the same with what we have in the matrix, the formula that we used previously. Okay, next, partition of a matrix. Partition of a matrix is basically divide matrix into blocks or submatrix. This particularly useful in simplifying matrix operations, and it can be applied to any matrix that can be divided into smaller rectangular blocks. The blocks behave almost like individual matrices within the larger matrix during operations such as additions, multiplications, and finding determinant. The concept of partitioning of matrix widely used, so that we need to understand that. So for example, here you have a general 3 by 4 matrix, and you want to partition it into a 4 matrix A11, A12, A22 and A11 12 21 22. Okay, so here, what is the partition of this matrix? Well, it depends. You can use, let's say this is A11, A12, and this is A22, this is A121, A22. Okay, but and normally we partition it is using equals value, so not really having difficulties like this. Okay. Next, a trace of a matrix, or denoted as a TR. Um, well, it's the sum of the element of the main diagonals from top left to the bottom right. Its property is a unix, because it can be used to many areas as well later on. So basically, trace of a matrix, let's say A here, this the sum of the main diagonal. So will be this one. Okay, but for this one, this will be the sum of this diagonal. Okay, so it's equal to this one. And another important things about matrix operations is to understand the property of matrix arithmetic. So it includes several key rules that become foundational to understanding on how matrix behave under various operations. For example, the first one is a commutative law. When you have additions of matrix A plus B, it will be equals B plus A. Okay, what is subtraction? Yes, this the same. And associative law is also applied. So when you A plus B plus C, you can do the first operation first, and then do the plus C later, or you can B plus C first and then plus A later. Okay, it's also applied for the multiplications. But for this one, when you have multiplication with something's addition inside of the bracket like this, it's applied the left distributive law, so you can do it like these operations. Also right distributive law, so B plus C multiplied by A like this, so you get B multiplied by A plus, and then later on plus C multiplied by A. Okay, and the rest is applied. Here A is a scalar value. Okay, small, this one scalar value. So we will need to see this one in action in more by doing exercise. Okay, example one of the exercise showing the uh, associative and matrix multiplications of matrix multiplication. So you have this one, matrix A, matrix B, matrix C. So when you multiply A with B, okay, and then B with C, okay, then if you do the AB and multiplied by C, will be equals to A and multiplied by B with C first. Okay, so this one, the B with C is this one, AB is this one. So this value, then you multiply with C later on, is equals to this. And if you do the B with C first, and then later multiply with A, you got the same value here. Okay, same. Next, however, when you multiply the matrix, be careful, because the order is a matter. When you A multiplied B with B, like this, you have matrix A and B, this one, it not going to be always the same with B multiplied by A. Okay, it is only the same when B is equals to inverse of A. Okay, but for this one, since B is not inverse of A, then it's not the same. Okay, Another concept you need to know is a zero matrix, when the value of entry of this particular matrix is equal to 0. And then next, zero matrix is also have unique properties, because there are several there are several properties that indicated to with the matrix zero only. For example, when you plus with zero, of course it will be the same with what it is. So this is several properties of zero matrix that you need to know. The additive identity multiplication of a matrix with zero, and so on. Okay. And the power of matrix refers to multiplying the matrix by itself a certain number of time. Okay. For example, this one, a multiplied by a power of n, it means that you multiplied by a up until n factors. And if a is invertible, we can define negative powers of a to be the power of minus n. So means what? Means the inverse to the power of n. Means the inverse multiplied by several times, n times. And besides that, we also have these three components. When we have a matrix with this power s and r and s, you can additive the power. However, when you have this one, a multiplied a to the power of r to the power of s, so you can do multiplication of the power. Okay. And then here's some uh, properties related to the inverse and power. So when you have a inverse is invertible, so when you have a inverse, you inverse it again, you get back to the original. Okay. So inversible of an inverse is same with the original matrix. The second one, the power, and when it's inversible, so a to the power of n, inverse it, you will have a inverse n times. Okay. And then k multiplied by a, when a is an inversible, k multiplied by a inverse, you can have k inverse, k to the power of minus 1 multiplied by a inverse. Okay. Okay, this is an example of the previous properties. You can exercise and try to calculating it. Okay. Next, the square of matrix sums. So it covers the concept in a linear algebra where it involves squaring of a sum matrix. So when you sum of two matrices by A and B is a square matrix. So A and B, when in arithmetic we know this concept, right? A plus B square is A square plus AB plus BA plus B square, and then this one, okay. However, in matrix arithmetics, we have no commutative law of multiplications. The best way you can do is to write a to the power of a plus b square is that a square plus b plus ba and b square. Okay, when ab is equals to ba, then you can have 2ab. But when it's not, this one, it's often not, so you can only write it like this. Okay. Okay, another one is a matrix polynomial, means that when you have a square matrix, let's say an n by n matrix, and then you have a polynomial functions like this. So this is the value of the variable x. Okay, then you can input the matrix into those polynomial function denoted by p matrix A, means that you input all this value to the variables of it. Okay. Okay, the example is like this. For example, if you have polynomial x squared minus 2x minus 3, you have matrix A here. Then if you are being asked to calculate polynomial of matrix A, then you input this one. So you have a squared minus 2a minus 3 identity matrix. Okay, don't forget the identity matrix. So here you have minus 1, 2, 0, 3 square, minus 2, okay, this one, and minus 3 of this one. So here the calculation of this, you have this one, this you have this, and you have 0. So the value of this polynomial matrix is 0. Next, transpose. Okay, uh, in general, when it's transpose, we have the we have this one, right? We earlier the row become the column, like this. Okay, since it's invertibles and AD minus BC is non-zero, uh, then the determinants of the matrix A can be verified by this one. Okay, so when you have a matrix can be transposed, when you transpose it and then inverse it, it will be equals to the inverse it first then transpose it. So basically this is just another properties, inverse of a transpose. Okay, now we talk about the last part of this materials for this slide. It's about elementary matrix and the row operations. So first, there is a definitions of row equivalence. Matrix A and B are said to row equivalence if either can be obtained from the other by sequence of elementary row operations. Elementary row operations I mentioned earlier: switching, uh, multiplications, and addition with another row. This is called row equivalent. So this concept is crucial to understanding relationship between different matrix form in order to solve linear systems like we mentioned earlier at the beginning. And second definitions is about elementary matrix. When you have n by n matrix, it's called n elementary matrix if it can be obtained by n identity matrix performing single elementary row operations. Okay, let's see the example here. Listed below are 4 elementary matrices and the operations that produce them. So this one, you can multiply the second row of minus 3. So this is an elementary matrix. Okay, so you multiply this one with uh, minus 3. Add 3 times to the third row, second row. Okay, interchange this one with the okay, this one first, maybe the second row and the fourth row. This one row 2 and this one row 4. You interchange it with each other, so it becomes identity matrix. I think this one should be divided or multiplied by 1/3. Okay, so you get 1 0 0 1 identity matrix. This one, it becomes, when you change this one with this becomes 0, this become 1, this become 0, this become 1. Okay, and for this one this one, add 3 times from the third row, row 3 multiplied by 3 to the first row. Okay, I think minus 3, so it become 1 0 0 0. Okay, okay, and then this one multiplied by 1. Okay, it's already elementary row. So if elementary matrix E resulting from the performing a certain row operation in IM, A is a M by N matrix, then EA is the matrix produce the same row performed in A. Okay. Okay, consider the matrix of this one, and then elementary matrix is this one. Okay, Now, when you multiplied E multiplied by A, then you will have this one. Okay. So basically, elementary row operations is the step-by-steps taken in order to gaining for the identity matrix. Okay. Um, I think this one, the final one, is the same with what we have previously. Here is the original matrix A, and here is the identity, and then you try to make this one identity matrix. This one will be the inverse of it. Okay, so the rest of it will be an exercise. We will try to discuss this in the class later on, and I hope you see these videos before the class.